Episode 22, titled BGP Design Thinking, Peering Intent, Policy, and Stability, we treat Border Gateway Protocol design as a set of policy decisions that shape route exchange behavior, because BGP is less about discovering the shortest path and more about enforcing the relationship you intend to have with another network. The exam often presents BGP as if it were a simple checkbox for Connect to Provider, but the best answers reflect that BGP is a negotiation tool that can either create stable, controlled reachability or accidental chaos depending on how policy is applied. When you design BGP well, you decide what you will share, what you will accept, what you will prefer, and what you will reject, and those decisions should match business intent and risk tolerance. BGP is powerful precisely because it can encode those choices in attributes and filters rather than relying on manual route entries everywhere. The flip side is that power increases the blast radius of mistakes, which is why stability and safety practices matter so much. The goal here is to make BGP feel like an intentional boundary contract you can reason about, not a mysterious protocol that just runs. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Peering intent is the first design question because transit, peering, and private connectivity relationships each imply different expectations about what routes should be exchanged and how traffic should flow. Transit relationships are about buying access to a broad set of routes, typically the wider internet, and they imply that you will learn many prefixes and will forward traffic out to reach many destinations. Peering relationships are about exchanging routes for mutual benefit, often to reduce latency, cost, or dependency, and they typically involve a narrower set of routes that represent each party's networks rather than the whole internet. Private connectivity between partners often implies an even narrower exchange, focused on specific enterprise prefixes needed for business workflows, and it usually comes with stronger expectations about stability and controlled advertisement. The exam sometimes hints at intent through words like provider, internet access, partner, dedicated link, or private connection, and those hints should drive your default assumptions about scope. If you misread intent, you can end up advertising too much, accepting too much, or preferring the wrong path, and those mistakes are exactly the kind the exam expects you to avoid. Clear intent is the foundation because policy should enforce the relationship, not fight it. Path attributes are how BGP turns intent into behavior, and a few common ones appear often in scenarios because they influence preference and propagation. Autonomous System Path, commonly spoken as AS path, reflects the sequence of autonomous systems a route has traversed, and it is often used as a loop prevention and general preference signal, where shorter paths can be favored. Local preference is an internal decision attribute used to prefer one route over another within an organization, making it a powerful tool for steering outbound traffic toward a preferred provider. Multi-exit discriminator, commonly spoken as MED, is typically used to suggest to a neighbor which entry point is preferred when multiple connections exist, acting as a hint that can influence inbound traffic decisions. The key exam-level point is that BGP does not just pick the shortest path. It evaluates attributes according to policy and tiebreakers, and those attributes are how you express preference. When a scenario says, prefer provider A unless it fails, you should think local preference for outbound selection and carefully controlled advertisements for inbound influence. Understanding the role of these attributes helps you pick answer choices that align with policy goals rather than expecting the protocol to guess your intent. A safe BGP design begins by defining what routes to advertise and which to suppress, because route exchange is the core contract, and anything not explicitly controlled becomes a liability. Advertising defines what your neighbor can reach through you, and you should only advertise prefixes you truly own or are responsible for carrying under the relationship. Suppressing is equally important because it prevents accidental exposure of internal networks, prevents unintended transit behavior, and reduces table size and complexity. In enterprise contexts, this often means advertising summarized prefixes for your public-facing networks or for the subset of internal networks meant for a private connection while keeping management and sensitive segments hidden. It also means being cautious about advertising defaults, because a default route is not just another prefix, it is an instruction that can redirect large volumes of traffic. On the exam, answers that assume you will just advertise everything are often wrong, because BGP is most dangerous when it becomes an uncontrolled broadcast of reachability. The best answers usually reflect deliberate advertisement and suppression aligned to relationship intent. Route filtering and prefix lists are the practical guardrails that prevent accidental leaks, and the exam often expects you to treat them as mandatory hygiene rather than as optional hardening. Filtering inbound determines which prefixes you will accept from a neighbor, protecting you from taking routes that are not appropriate for the relationship or that could destabilize your routing table. Filtering outbound determines which prefixes you will advertise, protecting the neighbor and the broader ecosystem from accidental leak of private, overly specific, or unintended routes. Prefix lists provide a clear mechanism to define allowable ranges, and they support a least privilege approach to route exchange, where the default posture is deny unless explicitly permitted. Filtering also supports stability because it reduces churn and prevents accidental redistribution of routes that should remain internal. In exam scenarios, especially those that mention providers, partners, or compliance concerns, correct answers typically include the idea of explicit filtering to limit scope. BGP design without filters is like a firewall with allow-all rules, and the exam tends to treat it as reckless. Communities are another key tool because they act as tags that carry intent across routing boundaries, letting you communicate policy meaning without rewriting every attribute repeatedly. A community is metadata attached to a route that can signal how the route should be treated by the receiving party, such as whether it should be advertised further, preferred, or handled in a special way. Communities are useful because they scale, allowing you to apply a consistent policy to many routes based on tags rather than on enumerating each prefix with unique rules. In provider relationships, communities often allow an enterprise to request actions like controlling propagation scope or influencing preference behaviors according to prearranged agreements. The exam may describe this indirectly as tag routes to influence provider behavior, which is essentially community usage in principle. The core idea is that communities help preserve intent as routes travel, reducing ambiguity at boundaries. When you can see communities as policy labels, you can interpret scenario choices more clearly. Convergence and stability in BGP matter because the Internet and large hybrid networks tolerate change poorly when changes happen too frequently, and dampening flaps is one mechanism that keeps paths sane. Convergence describes how quickly routing settles after a change, but with BGP, the bigger risk is instability caused by routes that flap repeatedly, creating churn that affects many devices and can amplify outages. Dampening is the practice of suppressing routes that change too frequently, reducing noise and protecting stability at the cost of temporarily preferring a less optimal path. The exam-level lesson is that stability is a design goal and not merely an emergent property, especially when you have multiple upstreams and complex policy. Instability can also be introduced by aggressive advertisement of many specific prefixes, by poor summarization, or by misconfigured timers that cause frequent session resets. In a well-designed environment, you want predictable behavior during failures, and you want changes to be deliberate rather than constant. Exam scenarios that mention intermittent reachability, frequent link flaps, or instability after changes are cues to consider how BGP stability practices and careful advertisement scope influence the outcome. A classic design scenario is building multi-homed connectivity with two providers for resilience, because it forces you to express intent about preference, failover, and what routes you share with each provider. In such a setup, you often want outbound traffic to prefer one provider under normal conditions while keeping the second as a backup, which is typically expressed through local preference and controlled route selection internally. For inbound traffic, you may want external networks to prefer one provider path toward you, which can involve how you advertise routes, how you summarize them, and what attributes or communities you use to influence upstream propagation. Resilience also requires that you monitor the health of each session and ensure that failover behavior is predictable when one provider path degrades. The operational reality is that multi-homing increases complexity, but it reduces dependency on a single provider and can improve availability when designed carefully. In exam terms, the best answer in a multi-home scenario usually includes explicit preference policy, strong filtering, and monitoring rather than simply connect to two providers and let it work. The exam is testing whether you know that two links without policy is just two sources of surprise. Security is part of BGP design because sessions are control plane relationships, and you should authenticate sessions and protect the control plane with limits to reduce both mistakes and malicious interference. Authentication ensures that only authorized peers can establish the BGP session, reducing the chance that an attacker or misconfigured device injects routes. Control plane protection includes limiting which neighbors can connect, rate-limiting control plane traffic where appropriate, and monitoring for anomalies such as unexpected route counts or sudden changes in advertised prefixes. Security also includes strict filtering because even an authenticated neighbor can accidentally leak routes, and the filter is what prevents that from becoming your problem. In hybrid environments, the boundary between enterprise and provider or cloud is a trust boundary, and BGP is one of the main places that boundary is enforced. Exam scenarios that mention untrusted partners, provider links, or unexpected routing behavior often expect you to include controls like authentication, filtering, and monitoring thresholds. The best answer is usually the one that treats BGP as critical infrastructure and applies the same defensive mindset you would apply to any privileged control plane. One severe pitfall is exporting default routes, because an exported default route can black hole partner traffic fast by causing a neighbor to send you traffic you cannot properly deliver. If a neighbor accepts your default, it may direct all unknown destinations toward you, turning you into unintended transit, which can overwhelm your link and create widespread reachability problems. Even if you have internet access, you may not intend to be the path for a partner's general traffic, and the relationship may not permit it, creating both technical and contractual issues. Default route export can also create loops if multiple parties export defaults to each other, producing a failure that is hard to diagnose quickly. The exam often hints at this risk by describing a partner link meant for limited business traffic and offering an option that advertises a default route, which is usually incorrect unless the relationship is explicitly transit. A disciplined design advertises only what is needed and treats defaults as exceptional rather than routine. Recognizing this pitfall helps you avoid answers that solve a narrow reachability issue by creating a broad, dangerous route policy mistake. Another pitfall is asymmetric routing, because BGP policy can steer outbound and inbound paths differently, and that asymmetry can break stateful inspection and confuse monitoring. Stateful security devices often expect to see both directions of a flow, and if inbound traffic enters through one edge while outbound return traffic exits through another, state tracking can fail, producing intermittent application failures. Monitoring and troubleshooting also become harder because logs and flow records may be split across different paths, making it harder to reconstruct events and to confirm whether a policy change caused a symptom. Asymmetry is not always wrong, but it must be accounted for, and the design must ensure that stateful enforcement points are placed where they can see the full conversation, or that the environment is built to tolerate asymmetric flows. In exam scenarios, if the prompt emphasizes stateful firewalls, strict inspection, or confusing monitoring, uncontrolled asymmetry is a likely hazard. The best answer often includes aligning routing policy with security placement or ensuring that inspection is designed for the path behavior you are creating. BGP gives you policy power, but that power must be coordinated with security architecture. A quick checklist helps keep BGP decisions safe. Intent, filters, attributes, monitoring, and rollback plan ready, because these elements prevent most catastrophic mistakes. Intent clarifies whether the relationship is transit, peering, or private partner exchange, which determines the scope of routes that should exist at all. Filters ensure you accept and advertise only what is appropriate, preventing leaks, unintended transit, and route table bloat. Attributes are how you express preference and influence path selection, and they should match business goals like primary and backup paths. Monitoring ensures you detect unexpected changes in route counts, session stability, and reachability, because BGP issues often become big quickly. A rollback plan matters because policy mistakes can have immediate impact, and you need a safe way to revert to a known good configuration without improvisation. Exam scenarios that mention stability requirements or high risk often reward answers that include this operational discipline. When you can mentally run this checklist, you can tell whether an answer choice is describing a safe BGP design or a risky one. To end the core with an attribute selection prompt, imagine you have two provider links and you want outbound traffic to prefer provider 1 while keeping provider 2 as failover, and you want inbound traffic to favor provider 1 when possible. For outbound preference, you would typically set higher local preference for routes learned from provider 1 within your routing domain, because local preference is the internal lever that guides which egress is chosen. For inbound influence, you might adjust how you advertise your prefixes, such as advertising more specific prefixes on the preferred link, or using agreed-upon community tags or attribute hints to encourage preferred ingress, while being careful not to create instability or excessive table growth. You would also ensure that filtering and monitoring are in place so that route counts and session health remain stable, because preference without stability is not a win. The best exam answer in this prompt is usually the one that uses the right attribute for the right direction, showing that you understand which levers affect outbound versus inbound behavior. It also usually includes the idea that influencing inbound is less deterministic and depends on the other party's policy, which is why safe design focuses on controls you own and monitor. In the conclusion of Episode 22, titled BGP Design Thinking, Peering Intent, Policy, and Stability, The central idea is that BGP is a boundary policy tool and must be designed like a contract rather than configured like a default route. You begin with peering intent, distinguishing transit, peering, and private partner connectivity, so route scope matches relationship reality. You use attributes like ASPath, local preference, and MED to express preference, and you define explicitly what routes to advertise and which to suppress so you do not become unintended transit or leak internal networks. Route filtering and prefix lists are mandatory guardrails. Communities carry policy intent across boundaries, and stability practices like dampening help reduce churn when routes flap. You secure sessions through authentication and control plane protections, avoid pitfalls like exporting default routes and creating asymmetric paths that break stateful inspection, and you keep a checklist of intent, filters, attributes, monitoring, and rollback readiness. Assign yourself one policy walkthrough by choosing a simple two-provider scenario and narrating step by step what you would advertise, what you would filter, which attribute would set outbound preference, and what you would monitor, because that narrative is the safe peering habit the exam is trying to build. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.